Beneath the hood of your car lies a machine that has powered the modern world for more than a century. And yet for most people, its inner workings remain a mystery. We call it the internal combustion engine, and while from the outside it may look like nothing more than a block of metal with a maze of hoses and wires, inside it is a precisely choreographed system in which every component plays its role with split-second timing. From a physics perspective, an internal combustion engine is a device that converts the chemical energy of fuel into mechanical energy through the controlled combustion of an air-fuel mixture in a sealed cylinder. In the case of a gasoline engine, this process follows what's known as the Otto cycle, and it is far more sophisticated than simply igniting gasoline with a spark. It's a complex sequence in which pistons, valves, the crankshaft, connecting rods, and ignition work together with astonishing precision. The history of the internal combustion engine stretches back to the 19th century, when early inventors struggled to create machines that were both practical and reliable. The breakthrough came in 1876, when German inventor Nicholas Otto patented the four-stroke engine, a design so effective that its core principles are still used today. This four-stroke or four-cycle process is made up of four distinct phases: intake, compression, power, and exhaust. Each of these phases takes place at a different point in the piston's movement, and the complete cycle requires two full rotations of the crankshaft, meaning 4 strokes of the piston, 2 moving up and 2 moving down. In the intake stroke, the piston moves downward, creating a vacuum inside the cylinder and drawing in the air-fuel mixture through the open intake valve. In a gasoline engine, this mixture is prepared in the intake system, either by a carburetor in older designs or, more commonly today, by a fuel injection system. In a diesel engine, only air is drawn in during intake, as the fuel is injected later during compression. Once the piston reaches the bottom of its travel, known as bottom dead center, the intake valve closes and the compression stroke begins. During compression, the piston moves upward, squeezing the air-fuel mixture into a much smaller space. This increases both its pressure and temperature, creating the ideal conditions for ignition. In a gasoline engine, the goal is to prepare the mixture for ignition by the spark plug, while in a diesel engine, the heat generated by compression alone is enough to ignite the fuel when it is injected. The compression ratio, the ratio of the cylinder's volume at bottom dead center to its volume at top dead center, is a key factor in an engine's efficiency and performance. In gasoline engines, it's often around 10:1, while in diesels it can be 16.1 or higher, producing such intense heat and pressure that no spark is needed for ignition. The power stroke is where the magic happens. In a gasoline engine, once the mixture is fully compressed, the spark plug fires, igniting the mixture in a controlled explosion. The resulting combustion forces the piston downward with tremendous power, and the connecting rod converts this linear motion into the rotational motion of the crankshaft. In a diesel engine, the effect is the same, except the ignition happens when fuel is injected into the hot compressed air. This power stroke is the only phase in the cycle where the engine actually produces mechanical work. The other 3 strokes are simply preparation for it. Finally, the exhaust stroke clears the cylinder of the spent gases. The exhaust valve opens, and the piston moves upward again, pushing the exhaust gases out through the exhaust manifold and into the exhaust system. The timing of valve opening and closing must be extremely precise, because if a valve opens too early or too late, power is lost or the engine can be damaged. This entire 4-stroke cycle repeats itself thousands of times per minute, with modern passenger car engines running anywhere from a few hundred RPM at idle to over 6,000 RPM under full throttle. Behind this seemingly simple process lies a range of highly engineered systems. The valve train, which controls the opening and closing of the valves, can be designed in many ways, from older pushrod systems to modern overhead camshaft designs with variable valve timing. Lubrication is provided by an oil system that distributes oil to all moving parts, while the cooling system circulates coolant through passages in the engine block and cylinder head to carry heat away and prevent overheating. Internal combustion engines generally fall into 2 main categories: spark ignition and compression ignition. Spark ignition engines run on gasoline and use spark plugs, while compression ignition engines run on diesel fuel and rely on high compression to ignite the fuel. Each has its strengths. Gasoline engines are typically lighter, smoother, and can rev higher, while diesels offer greater fuel efficiency, higher torque at low RPM, and longer service life. In addition to four-stroke designs, there are also two-stroke engines, which are mechanically simpler and have a higher power-to-weight ratio, but tend to be less fuel efficient and produce more emissions, so today they are mostly used in motorcycles, scooters, outboard motors, and small equipment. Even with the growing shift toward electric vehicles, the internal combustion engine still has its place, not only because of existing fuel infrastructure and fast refueling times, but also because of its proven durability and adaptability. Modern engines are far cleaner than their predecessors, thanks to innovations like electronic fuel injection, turbocharging, catalytic converters, and particulate filters, all of which work to reduce harmful emissions. So the next time you turn the key or push the start button, remember that you're setting in motion an incredibly precise mechanical dance, one that turns the energy locked in fuel into the movement of your wheels. And while the future of transportation may be electric, understanding how the internal combustion engine works is to understand one of the greatest engineering achievements in human history. Subscribe us for more videos.